Hey everybody, let's take another look at a relative velocity problem, but this time we're going to be in 2 dimensions. And so I've set up a problem here. So let's assume I've got an airport here in the city of Dover, and there's an airplane here, or a jet, and that jet's going to fly out of Dover. And I'm going to tell you that the velocity of the jet, and this should be a vector quantity, the velocity of the jet with respect to Dover, which is a stationary point, that's the city, right? That's where the airport is 250 kilometers per hour in the j-hat direction. Now, up here is y, that's the j-hat direction. Oftentimes this will also represent north, and this would represent east, if you will. Right? So kind of keep that in mind. You have north, east, south, and then west. That would be positive y, positive x, negative y, negative x, respectively. All right, and you could designate it differently if you want to, but that's a fairly standard compass direction. Then I'm going to tell you that there's a wind blowing. It's to the west and a little bit north. So the wind is blowing at a speed of negative 25 kilometers per hour in the I-hat direction, that's to the west, and then 15 kilometers per hour, let me just even put a W there, and then 15 kilometers per hour in the j-hat direction, that's north. So the wind is blowing in this direction. What I'm interested in then is what is going to be the velocity of the jet with respect to and I need to change this. This is actually wrong. The velocity of the jet with respect to the air is 250 kilometers per hour j-hat. Okay, so I have to undo what I said before. That's all right. That's the velocity of the jet with respect to the air, because airplanes are measuring air speed, right? And so I'm the pilot here. I'm going to point the airplane due north, and I'm going to take off due north at 250 kilometers per hour once I've lifted off of the ground. So I'm no longer with respect to the ground because the ground is stationary, and the air, that's what I'm flying in. That's my medium of transportation, is moving. But what I'm interested in is the velocity of the jet with respect to Dover. In other words, the tower at Dover is going to see the plane moving at some velocity. What is that velocity? All right, let's go back to the one-dimensional problem that we did last time. This is equal to the velocity of the jet with respect to the air plus the velocity of the air with respect to Dover. Remember that we look at the subscripts when we add the two vectors together. When we add, subtraction, it's different because there's a minus sign and you reverse the subscripts, but let's not go there. Jet with respect to air, air with respect to Dover, the airs cancel, and I'm left with the jet with respect to Dover. And so this becomes the velocity of the jet with respect to the air, which is 250 kilometers per hour, and that's in the j-hat direction, plus a negative 25 kilometers per hour in the I-hat direction, plus 15 kilometers per hour in the j-hat direction. I'll put that in parentheses. And so when this is all done, I get 220, no I don't, I get negative 25 kilometers per hour I-hat plus 265 kilometers per hour j-hat. And that would be the velocity of the airplane with respect to Dover, if you will, right? The fixed ground. And that's going to be looking something like this, minus 25 in this direction, 265 in that direction. Right? And so there'll be an angle here. If I measure, generally in aviation, we measure with respect to north. Well, it depends on who's closest. This is the angle I'm going to be interested in. And then the speed will be the sum of these, right? So the sum of the square is square root. So the speed of the plane, the velocity of the jet with respect to Dover, magnitude will be negative 25 kilometers per hour squared plus 265 kilometers per hour squared, square root of all of that. And then the direction, if I call this angle theta, theta will equal the arctangent of 25 kilometers per hour over 265 kilometers per hour. The arctangent of that. And the way I'm going to state that, because theta is west of north, so whatever number of degrees this is, it would be that many degrees west of north. Okay? So the question is, what are those values? Let's find out. And so if I did my calculations correct, I'm going to end up with a speed down here. So let me just say the velocity of the jet with respect to Dover. This might be like polar form. 266.2 kilometers per hour. Probably more digits than I need. At an angle, right? And so I'm going to call it 5.39 degrees. And I'm going to say west of north, right? West of north, because I don't want to just say 5.39 degrees because that implies with respect to the positive x-axis. When we talk about motion like this, oftentimes the compass direction is what counts. All right, so there's a fairly simple example in 2 dimensions. Okay, next time around we're going to do a slightly more complex example. Still 2 dimensions. We'll stick with these drawings, but we're going to try and figure something else out. Okay, stay tuned. If you have any comments or questions, leave them in the comments box below. Thank you.